Okay, so today in today's class we are going to discuss about solving Cauchy initial value problem for Quasilinear first order PDE. Actually, this is the first class, so we will merely start with the theory, and perhaps in this class, on the next class, we will continue on specifically solving the problems. Okay, so as we have learned the same thing for the linear and semi-linear first order PD, but as we go on, you can easily understand there are some fundamental differences, though the strategy is almost similar. If you consider solving the problem skills, they are almost similar, but there are some fundamental differences which will come once we consider quasi-linear first order PDE in comparison with the semi-linear, and also the linear is included there, semi-linear first order PDE. Okay. So first and foremost of all, let me consider the standard form. This is the standard form, if you remember that, for the first order quasi-linear PDE. And what is the change? We all know this is now A, B, C are functions of not only not only C, but A, B are functions of not only X, Y, but also U. C is also a function of X, Y, U in both semi-linear and here also. But the change is lying in A and B. Okay. Now for the analytical assumptions, I am not going into the details of it. I just assume that all this A, B, C are belonging to C1, that is there. They themselves are continuous and their first order partial derivatives are also continuous. Okay. And they are these functions, continuous functions in some space of X, Y, U. Let us name it as D2, which is a subspace of X, Y, U space. Okay. Subspace of X, Y, U. As I already said, I'm not going into the details of why we are taking this and everything. I'm just concerned about just designing, or rather discussing about how to solve this quasi-linear first order PDE. So you can easily understand from here, first of all, irrespective of this PDE and everything, if U xy is any surface, no U0, then what are the direction ratios of the normal to the surface? They are nothing but ux, uy, and minus 1. In 3D, I am considering only. So this is the direction ratios of the normal. DRS of normal at any point to surface at any running point P, at any point pxy. Okay. xyu obviously, because as we are considering three-dimensional surface, so obviously three-dimensional object, so definitely function for any point is now having three components. Okay, so now you can easily understand if it is direction ratios of the normal to the surface, and normal is always perpendicular to the tangent at that point P to the surface, and you can consider, if we are speaking of surface, then at any point we can consider there is a tangent plane at that point, so that in the tangent plane there are infinitely many tangents drawn to the surface at part passing through that point. That means this is the tangent plane at some surface, this, say, point P. Okay, and this is your surface U, this thing uxy equals to u0. Okay, and you have picked the point P. So through P, I can draw infinitely many tangents, right? All lying in this tangent plane. So whenever I am saying any vector is perpendicular to the surface, that means any vector is perpendicular to the infinitely many tangents passing through that point P on the surface. So now if you just observe what was the equation given to us, this was the equation given to us, right? So if I consider, say, I consider V as a vector having three components A, B, C, then equation 1 can be rewritten as, or rather interpreted as, not rewritten, but interpreted. Equation 1 interpretation can be like this, V dot Ux, comma Uy minus 1 equals to 0. Okay, so what does it mean? This is perpendicular to the surface, and it is perpendicular to this vector. That's why you are getting the dot product to be 0. That means this is perpendicular to this vector. That means normal to the surface is perpendicular to this vector. That means V is any direction tangential to the surface. Now you see whenever the problem is provided to us, we already have information about A, B, and C. So, and what is our task? we are just trying to find out either general solution, or if it is a Cauchy initial value problem we are talking about, then a particular solution containing the initial surface or initial whatever the data is given to us. So that means at the very outskirt, our surface is any surface which is having v as a tangential direction to it at any point px. So that allows us to give the definition of the integral surface as that. Now we know integral surface is any solution surface to the given PD. That means if I say u is equals to u0 is integral surface is of 1, then definitely u equals to u0 satisfies 1. That is the standard notion of integral surface. Now, from whatever geometrical interpretation we just now developed, we can say कि surface, let me just call it roughly definition of integral surface, okay, surface uxy is a solution, or rather integral surface is, I'm writing in short is, of given PDE of equation 1, where if and only if for every point on the surface, the tangent plane contains the direction v. The tangent plane contains the direction, I won't say v because v is my naming I have applied here. So A, B, C. Now it has a very specific name in the theory of partial differential equation. This v is said to be the Monge's direction. So in our definition, the definition reads as this: contains the Monge's direction as a tangential plane. Okay. That means, let me read it out again. Surface uxy is a solution integral surface of equation 1 if and only if for every point on the surface, the tangent plane contains the Monge's direction. And Monge's direction is already known if you know the partial differential equation. Okay. Because this is the Monge's direction, ABC. Okay. And now, this is a Monge's direction. Now, using this Monge's direction, you can easily understand if I consider in 3D now. Sorry, let me draw it separately. Here. Okay, you are considering any curve, three-dimensional curve, not in xy plane anymore. I am not talking about only xy plane, xyu space rather. I repeatedly saying it. So here, if you consider any curve, say I name it as say gamma or anything. So at any point P, coordinates x, y, u. Okay, and also let me consider it as a parametric curve. Okay, so x equals to x sigma with parametrical sigma, then I can write it as this. Okay, so you can easily understand that along the curve or at any point on the curve, we can get the variation of x as dx d sigma, dy d sigma, and variation of u as du d sigma. Okay, and if we consider the tangent direction, then they are given by AB, that means ABC. Now, if I am saying this is my tangent direction, so suppose this is the curve, I have drawn the curve in such a way that V is a tangent to the surface, then the direction ratios of the tangent to the surface can be given again by dx d sigma, dy d sigma, du d sigma as three components. So they should be equal to what? A, B, and C. That means dx d sigma, dy d sigma, dy d sigma, du d sigma, this should be equal to V. Okay, so this is the direction of the tangent once you are considering as whatever is given to you, and another in differential form. Okay, considering the curve gamma. Okay. So this curve is referred to as, this curve gamma is referred to as Monge's curve. So what is the specialty of Monge's curve? I can define it as using Monge's direction. Here, from there only it is fetching the name, because any curve which is having at any point of it Monge's direction as a tangent, that is a Monge's curve. Because Monge's direction, if that Monge's direction means what? According to our notation, it is ABC. If it is a tangent, then definitely for any point P, if I consider a tangent and try to find out the direction ratios, they will be given by dx d sigma, dy d sigma, du d sigma. But again, you are saying that at any point P, x, y, u, the tangent to the curve is given by V. So this one should match with this one. That is what we are writing individually as a three components. So let me define the Monge's curve. Monge's curve is space curve. This curve is, as we are working with the three-dimensional space, entire three-dimensional space right now. Space curve whose tangent at any point P, x, y, u coincides with the Monge's direction is said to be the Monge's curve. Is said to be, Monge's curve, right? So Monge's curve is determined how? It is determined. That means if we want to find out Monge's curve, how can we do it? Solve these three equations. Solving these three equations. dx d sigma. Let me write dx d sigma, dy d sigma, and du d sigma. So, du d sigma. So from here, you can easily understand, I can couple these three up to write down this. Okay. So if you find out solution to these three ordinary differential equations, solve these three ordinary differential equations, you will get Monge's curve. Now you can easily understand from here a very crucial thing, and right now I also want to compare it with whatever we have learned in the semilinear case or the linear case. If you just recall it back, whatever we have learned, then you can see there we first dealt with the characteristic curves, right? Because there was everything dx d sigma, dy d sigma, AB, there was explicitly functions of x and y, but here they are involving x, y, u. Okay, so if you recall, the characteristic curves, for solving the characteristic curves, we never required this u, because A never involved u, B never involved u. So just combining these three, we find out simply f of x, y, c equals to 0. This were the characteristic curves. And we never paid any heed to the whatever the du d sigma will be, and we considered it as the compatibility condition, and we solved it separately to find out how will u be heading on the characteristic curve, or how the u will behave on the characteristic curve. But for finding out the characteristic curve, we never needed this u. Okay, but here in the Quasilinear case, first of all, I never till now I have said characteristic curve, right? I have said Monge's curve. Why? The reason will be clear just after a few minutes. So let us suppose we have changed the name from characteristic curve. We are saying Monge's curve right now. So for the Monge's curve, you can see the strategy is almost similar. Here also we are solving differential equations. There also we solve ordinary differential equations. My mistake. Here also we are solving ordinary differential equations. There also we solved it, but there we solved separately this dx d sigma, dy d sigma once, and this one separately. But now we have to solve all these three together, because now we need the information of u to find out the Monge's curve. I cannot neglect it. Okay. So now if I solve it, what I am supposed to find? You can solve first of all to find out some f of x, y, c1, or u may be involved there. And again, say suppose f1. And then again, another one, x, y, u, c2. So that means actually this Monge's curve is a two parameter family of curves, not a single parameter, but two parameter family of space curves. I'm not repeating space curves because of whatever we are speaking here, I cannot limit myself to the xy plane. You can easily understand because we have to take consideration throughout the use value. Okay, so two parameter. Why? Because one for C1, another for C2. So if I want to express these curves as parametric equations, how shall I write it? If I want to express this as parametric equations, then I have to write something like this. Let me write it. X equals to, so let me write what I am trying to do, expressing Monge's curve as parametric equations, parametric curve. Okay, so for the parametric curve, as we know key to express the point changing along the curve, for I say this is my curve. This is your, let me just draw it again. This is your XY space. Whatever you may consider, no problem in that. I'm not worried about it right now. So this is some your curve. So along the curve, if you move, going on, moving on, or going on, walking on, some parameter should vary. Let me consider that parameter to be sigma. So it is describing any of the curve. Now, as I said, this is a two parameter family of curves, means you are going to get many of these curves such that there are two special properties via which you can identify a single member from this family. So for any member, sigma is varying, right? Because it is describing every individual curve. Sigma describing every individual Monge's curve. Okay, let me write it here. Every individual Monge's curve. But C1, C2 variation, C1, C2 variation implies change or variation in or from one member of the family to another, from one member of the family to another member, to another member, to another member, right? So I am taking right now into consideration three variables, sigma, C1, C2, or I can, if I want to write like eta 1, eta 2, that means just the variation. I am writing all this in sigma eta form. Then I can write any point on Monge's curve, and that will give me what? That will give me the parametric equation, obviously, because if x, y, u variation, you can write that is all, actually you are trying to consider how the locus of a point is changing along a curve. So simply let me write it down, sigma, or let me stick to the C1, C2 only, y, this, and also then the u will also change. So u, let's pick C1. So this is your Monge's curve, MC curve expression in parametric. As I said, sigma will vary along the curve, C1, C2 will vary across the curve. Sigma varies along a curve and C1, C2 vary across curves. All are we are talking about Monge's curve. Okay, MC. So this is how we present Monge's curve. And if you just again recall back the scenario or the situation which we have faced while solving the semi-linear partial differential equations, obviously first order, then we had something like this for the semi-linear case, where something like this, x as some function of sigma c1, y as some function of sigma c1, and again u as some function of sigma, and this varied sigma c2. Okay, but now what I am saying, I have two parameter family of curves, not a single one. So if I fix use and another thing you see from here. So I am from one parameter family. I am moving to two parameter families. That means from characteristic curves, I am moving to Monges curve. Okay, and that's why I already said this is coming because we have to solve three ordinary differential equations coupled together. I cannot solve separately as we did in semi-linear case. Now from here, if I say I am projecting Monges curve MC on XY plane, then that means what? That means I am fixing some use value. Say u equals to u0. Say, well, u equals to u1. If you put u equals to u1, you can easily understand from here. Okay. Once I put u equals to u1 here for the, sorry, for this part. Once I fix equals to u1 here, then you can, once by eliminating this, or rather change the eliminating the sigma, you can easily find can x and y will again be function of this two parameters. Okay, so that means I can write then the projection of Monges curve on the xy plane, fixing some use value, will give me characteristic curves. Characteristic curves. Okay. This will give me the characteristic position of Monges curve on the xy plane, the characteristic curve. Okay. So again, you can see there that those characteristic curves, as we know, these will be xy curves. No u will be involved. These are xy curves. That means, let me write more specifically, some function of xy c equals to 0. There will be no u involved because you have fixed some use value, you have fixed some information about, given some information about you, and depending on that information, you are refining whatever knowledge you had on this Monges curve. So once you fix this u here, definitely this xy can be arranged as a function of sigma and c, one of the parameter, one of the arbitrary constants. So from there only I can say these are the characteristic curves. There is xy curves that is residing in the plane of xy. Okay. So now let us use the initial, whatever initial value is applied, because we are ultimately dealing with Cauchy initial value problem. So definitely some initial data is there. Initial data is applied to us. Now another interesting difference comes here. Whenever we talked about semi-linear case, we always said about data curve. Initial data curve, or I sometimes refer to either the datum curve. Okay. But here you see it is the initial data surface. Why? Because what is given, provided to us, it is provided x equals to some, say, function of this, y is equals to, and also u is equals to. Okay. So it is a 3D, three-dimensional case we are dealing with, and we are having two parameters here, eta 1 and eta 2. And if two parameters are there, it's a 3D. So definitely it is a surface you are talking about, not a curve. Okay. Now, as we did earlier, another thing, let me just mention it here, though we won't go into the justification of it. This curve, this initial, this surface, the initial data surface, capital gamma, initial data surface, is such that it is in D2. Remember D2, those ABC were functions of C1 defined in D2. We said at the very beginning. So there is a subspace of XYU, subspace of XYU space. That is the entire three-dimensional space. D2 is a subspace. Okay. So there I am taking this initial data surface and such that this is one, it is in D2, and another one, it never touches Monges curve. It nowhere touches Monges curve. Monges curve. That means what? we know what touch and Monges curves means. The Monges curve will never be tangent to this initial data surface. Monges curve will never be tangential to initial data surface.